Hey guys, we're going to do the next lecture in this module, which is on water. So let me share my screen with you. Give me just 1 second. Okay. And move stuff around. But here, okay, you can't see all the stuff I'm talking about, but I'm moving stuff around on my screen. So let's go ahead and do the pre-lecture assignment. You should have read pages 24 through 26 before hopping on to watch this. I'm going to assume that you did. And let's start filling out the answers. In water molecules, the electrons spend more time circling the oxygen atoms than the hydrogen, because oxygen's just cool that way. This makes the oxygen atom slightly negative in charge, just because the electrons are hanging out a little closer to it, and the hydrogen's atoms are slightly positive. These are partial charges, so it's not like what you'd get with an ion, okay? These partial charges with the oxygen and hydrogen makes water a polar molecule. Polar because it kind of has a positive end and a negative end, the poles, right? Okay, so then we have that third bond I told you we wouldn't talk about in the chemistry section. We're talking about it in this section, and that's the hydrogen bond. When the slightly positive charged hydrogen of one molecule is attracted to the slightly negative charged oxygen of another molecule. So in this image, all of these dashed lines, there's a ton of them, these are all hydrogen bonds. And as you can note it, or as you can see, you get this kind of spider web effect of molecules all attached to each other, okay? All right, this type of bond is relatively weak. It forms and breaks easily. And remember that when I say, or when we use the terms strong or weak for bonds, we are talking in relative terms. Weak as far, like when compared to a covalent or an ionic bond. I mean, I like to think of this bond as being flexible and that it can break apart but reform pretty quick. And it has to happen that way because if hydrogen bonds didn't break apart, water couldn't heat up, right? So weak that way, but strong enough that water sticks together in cohesion. So like if you're drinking out of a straw, all of those liquid molecules, water-based, hook on and stay held on to each other. Thanks, hydrogen bonds. So remember that weak, strong with bonds is kind of a relative term. All right, matching these. The high heat of evaporation. This is E. I just kind of said water boils, it evaporates because heat is released. As you add heat to water, it makes those water molecules move around quite a bit. All that movement finally breaks the hydrogen bonds and water can change state from a liquid to a gas, heating up as it does. Cohesion and adhesion, this is D. Water molecules cling to one another and other molecules and surfaces. Just going to talk about that with the straw thing. High heat capacity, this is B. Hydrogen bonds help water absorb heat without a great change in temperature. Again, this is like with E, the high heat of evaporation. It's because of the high heat capacity of water. Universal solvent, this is C. Since water molecules are polar, they can pull apart or dissolve other molecules. Like if you dump some salt into water, those crystals dissolve. And that's because the positive ion, which is the sodium, is attracted to that partially negative oxygen in water. And the negative chloride or chlorine is attracted to that partial positive hydrogen charge of water. Okay. Frozen water density. This is a frozen water or solid water is less dense than liquid water. Allows water to float on the surface and keeps things in lakes and ponds from dying. Because if water froze from the bottom up, everything in that would die. Okay? All right. Well done. Moving on. All right, why these are important for life. And again, this assumes that you're in a class. I'm just going to talk about them. Okay, so high heat capacity. How is this important for life? Just going to kind of bullet point a couple of ways here. First off, it keeps the earth temperature fairly constant. All those bodies of water mean that temperature stays fairly constant. This doesn't mean that there's not temperature fluctuations. Obviously there are. You can have temperature ranges though that are normal for an area. Another thing that's important with this, not only does it keep the Earth's temperature fairly constant, but our body is mostly water, so it keeps our temperature fairly constant as well. Which is important because if we get too hot, our cells start to break down. It's a bad thing, it causes death. All right, high heat of evaporation. This is important in sweating. This evaporative process is a cooling process. Helps again to keep our body temperatures constant. Okay. This is also kind of another environmental control effect, or the high heat of I can do this. The high heat of vaporization is also something that helps to keep ecosystems at a stable temperature. Okay, frozen water density, kind of already talked about this one too. Fresh water. Freeze from the top down so that everything inside stays alive. Okay. When you get a layer of ice across the top of a body of water, that ice actually acts as like a blanket as well. So it keeps the temperature of the water below stable, and it allows everything to live. Okay. Let's see, universal solvent. Talked about this a little bit in the sense that the polar nature allows water to pull things apart and to break things apart. This is important for hydration for our bodies. And it's also an important part of the, what do I want to say? Regulatory processes when it comes to like kidneys and urine and disposing of wastes. Cohesion and adhesion, this is going to be important for plants, as I've said, because it allows plants to defy gravity. So when you water a plant, you don't water the top and then it runs down. You water the bottom and it runs up. It doesn't really run up, but you know what I mean? Okay, so it allows plants to defy gravity, but this is also important in what happens to our lungs and our chest cavity when we breathe. And we'll actually get into topics like that with our lungs, and then also with the kidneys and the regulatory processes as we move through this semester. So this will come up again, if you will. Okay, so these are some illustrations here of the inner chest wall, water molecules that are kind of in between the chest wall and the lung. I'm not going to go into the details on it right now. Just remember this is an example for the quizzes, the test. Plants, again, water goes from the roots to the shoots, goes up against gravity. Okay. And then this is an example of solvent capacities because of polar nature. Okay. Why does your nose run when you cry? I don't know if you've ever wondered about that. But since it's the question of the day, it means it will probably have a high likelihood of being an extra credit question on one of your midterm exams. So here's the answer. It's basically because when you cry, the tear ducts in your eyes pull away the excess tears, the tears that aren't coming out of your eyes, and it drains them back through your nose, down through your nasal cavity, right? And so because of the whole adhesion, cohesion thing, those molecules of water that are part of the tears stick together and drain together out of the nose, making nose run when you cry. Okay. All right. Moving on. So to review the bond strength again in relative terms based on comparisons between the bond types themselves, the strongest bond is going to be our covalent and ionic, and then hydrogen. And we often think about covalent bonds as being shared electrons. Ionic, think of as being transferred. Okay, those look like bees. They're ours. All right, water molecules. Water is H2O, right? Well, water can break apart or disassociate. When water breaks apart, what we end up with are two different things. We have a hydrogen ion, which, if you notice, is positive, and a negative hydroxide ion. The hydroxide ion has the oxygen and one of the hydrogens and the electron that came from this hydrogen ion. Okay, this is positive because the electron from that hydrogen is over here attached to this hydroxide ion. Okay, so hydrogen has, again, hydrogen's weird. It has one proton and one electron and no neutrons. So a lot of times when you see an H plus, it's really just representing a proton and saying that that proton has come from a hydrogen atom that has gotten rid of its electron. Okay, makes sense? Again, what happens to hydrogen's electron? Well, it goes and hangs out with the hydroxide ion. So you have H plus, whose electron is going to go to our oxygen, and our other hydrogen attaches to it, and that's where we get the negative charge on this. Okay. All right, an acid. Give me a second to write this. Okay. When you add water to an acid, the water is going to break that acid up, releasing a bunch more of those hydrogen protons. Okay. And a base is going to do the opposite. Water is going to break up the base, but rather than releasing hydrogen protons, it's going to release a bunch of hydroxide ions. Equaling an increase in hydroxide concentrations. Okay. All right, so why is this important? Well, basically, water can kind of help to, when needed, keep things balanced pH-wise. Water itself is pH. Here's the question, why is water neutral? Because of how water can dissociate, right? So it has this positive hydrogen atom, and then you have the negative hydroxide ion. That's what makes up water, your H2O, but those charges cancel each other out, which is what keeps it neutral. Okay. A little bit more about pH here on this next slide. Maybe. There we go. So let's talk about pH. There's a couple things to remember about this. pH is actually measuring the hydrogen proton concentration in a substance, in a solution. Okay. So a pH of 7 is considered neutral. Anything below 7 is acidic. And above is basic. Now, the wording on this can sometimes be confusing because when you're looking at this pH scale to the right, this thing right here, When we look at something below 7, we can think about going down below that way. In which case you're like, that doesn't make sense. If it's below 7, it's clearly basic. No, they're talking about numerically below. Okay, so if this were laid horizontally, in some ways it would be easier because you could see that numbers that are lower than 7, below 7 that way, that's acidic. Above 7 numerically, that's basic. Okay. All right, so each unit, as you move up, is 10 times more acidic or more basic than the previous unit. Okay, so this is by tens, which makes figuring it out a little bit simple. Let's do an example. So if I go from a pH of 6 to a pH of 5, what's the difference here? What's the change difference? Well, we know that first off, we're going from a 6 to a 5, we're going down numerically, so we're getting more acidic, but how much more acidic? Well, we are getting 10 times more acidic. Okay, the pH 5 is 10 times more acidic than the pH 6. Okay, but now what if I go from a pH 7 to a pH 5? Well, let's look. Okay, so here's 7, which is our neutralish. We're going numerically down, right? So each jump down, 1, 2, is a difference of 10. So we're going to have a pH of 5 is 100 times more acidic than a pH of 7. Okay, does that kind of make sense? And then if we did a pH of 8 to pH of 5, same thing, because now we're going to have 1. Oh, I'm sorry, I started that in the wrong spot. Ah, that's a 5. That's a 5. All right. If we started that here, 1, 2, 3, add up the zeros, essentially, now you're at 1,000 times more. Okay. That's really all there is to it. All right, obviously you can't be in a group of 2 unless, as we've discussed in previous lecture, you'd like to invite your date, your roommate, or a family member over to do this with you. Which is more acidic or basic, which has more hydroxide ions? If you want to do this as practice, awesome. Just pick the 2 different pH values and do what we just did together, okay? So human pH is maintained at 7.4, very slightly off the total neutral, right? pH is normally maintained for humans in a range between 7.35, 7.35 and 7.45. And doctors will often use the pH of your blood to help diagnose certain conditions. If your blood is more acidic, that can mean you have one set of issues happening. If it's more basic, there's another. They're not all serious. It's just, it can give insight into what's happening in your body if you're looking at acidity of blood. So in order to keep things pretty neutral, 7.4-ish, in the human body, we have a variety of things called buffers. And these buffers are just there to keep the pH constant, keep it where it belongs, okay? So some of those buffers, again, going to help keep pH constant. Okay, So that means that in order to do that, they'll either take up or pick up. Take up or release or protons, or take up or release hydroxide. Okay, so let's say that the blood is getting too basic. That means we have too many hydroxide ions out there. Buffers will kind of have the ability to either pick up some of those extra hydroxide ions or release extra protons, hydrogen ions, in order to make that come back to balanced. So an example of this is the blood buffer in humans, which is carbonic acid and the bicarbonate ion. I'm trying not to write sloppy. Okay. So here's my carbonic acid, which is our H2CO3, right? Well, H2CO3 breaks down into a hydrogen ion and our bicarbonate ion. So when it says carbonic acid, bicarbonate ion, this is where that bicarbonate ion comes from, okay? And then you can put or add back together your hydrogen ion and your bicarbonate ion, and you'll reform carbonic acid. That's why the arrows go both directions here, because both things can happen. Carbonic acid can either dissociate into those two parts, or those two parts can come back together to reform carbonic acid. And in this way, it constantly regulates the pH of the blood, okay? Because if, let's say that our blood is more acidic, meaning it has an excess of hydrogen ions, okay? Too many. So it's more acidic. What happens is this bicarbonate ion is going to go find those extra hydrogen ions and bind to them, okay? So our bicarbonate ion plus our extra hydrogen ions hooks together and reforms carbonic acid, okay? To bring that pH back to a neutral level, okay? So if you kind of think about hydrogen ions and bicarbonate ions as buddies, right? Always looking out for each other. So if bicarbonate ions are like, hey, there's way too many hydrogen ions, I better go grab them, make sure that, keep them under control, then that's going to neutralize the blood pH because it's taking those hydrogen protons out of circulation. But hydrogen will do, well, carbonic acid technically will kind of do the same thing. If something gets too basic, it'll be like, whoa, we got way too many bicarbonate ions happening out here, so we need to release more hydrogen protons by breaking apart so that more hydrogen protons are present to balance out the blood. Okay. All right. I thought we had one page left. We don't have one page left. That's the end of that. Okay. Buffers are covered, especially the carbonic acid buffer is going to be covered on, let's see, the quizzes and the midterm, but especially the midterm. In fact, you might not have it on the quiz, on those little quizzes that you do through the textbook, but it will be on the midterm. So if you have questions about how those buffers work let me know. You kind of have to think about in terms of if this is too acidic with the carbonic acid, what needs to happen to make it more basic? Are we going to be breaking apart carbonic acid, or are we going to be forming it? Well, we're going to be forming it because we need those bicarbonate ions to pick up the acid and neutralize it. Okay, and then vice versa if it's too basic. All right, as always, let me know. Reach out if you have any questions, concerns, or need me to go over anything in more detail. And I will see you for the next lecture.